Greetings. Welcome to Electronic Circuits 1. This is lecture number 9, and I am Razavi. Today we will talk a little more about examples of diode circuits and how we analyze them. And then we will look at some real-life usage of diodes. We will look at some circuits that perform interesting and useful functions in devices around us. Before going there, let's take a quick look at what we covered last time in lecture number 8. So we saw in lecture number 8 that in analyzing diode circuits we must follow three principles. The first principle is we begin with an assumption regarding the state of each diode. Some diodes might be off, some diodes might be on. We just have to make an assumption, preferably an intelligent, educated guess regarding the states, and then write these assumptions down before we analyze the circuit. What should happen is that the final results that we obtain in terms of voltages and currents must agree with the assumptions that we made at the beginning. Now, in addition, what we noticed was that if a diode is about to turn on or off, it must have a voltage equal to VD on across it, assuming a constant voltage model, and its current must be small because it is just about to turn on or off. That's a very important point to keep in mind when we are analyzing diode circuits. And finally, the third point was that if a diode does carry a current, that current is allowed to flow only from the anode to the cathode. So if our analysis eventually gives us a current that is flowing from here to here, that is incorrect, and that results from an incorrect assumption at the beginning, or maybe somewhere along the line in our analysis we made a mistake, but that current cannot happen. So long as we remember these three principles, we can perform analysis systematically and correctly. All right, so let's go on to today's lecture. And in today's lecture, we will look at one or two examples of a little more complex diode circuits, again, just to improve our skills in analyzing and understanding what these circuits do. And then we will go and look at some practical circuits incorporating diodes. All right. So in this example, we actually start out with what we analyzed last time. If you remember, we had a circuit that looked like this. We had a diode D1 And this went to a resistor R1 and then a battery called VB. So this circuit was something we analyzed last time. We found the input current as a function of the input voltage, and we found the voltage at this node, which we called node N, this voltage, as a function of this voltage. And we plotted these from minus infinity to plus infinity. Okay, today we'll just twist this a little bit. We will add one resistor to the circuit from here, node N, to ground. So this is R2 to the bottom rail, R2, and this is node N. So we have one more resistor, and we will perform the same type of analysis. So in the first step, we would like to apply a voltage here called Vx and measure the resulting current Ix as Vx goes from minus infinity to plus infinity. Okay, once we add this resistor here, things become a little more interesting, a little more difficult. So we have to be more careful. But the principles I mentioned before still hold. Our methodology still holds. We just have to be more patient with our steps. Very well. So again, Vx is equal to minus infinity when we start out, and we would like to see what the circuit looks like under that condition. So if Vx is very negative, that means close to minus infinity, then what we expect is that D1 is off, because this voltage is, let's say, minus 5 volts with respect to this voltage, or minus 10 volts, or minus 100 volts. Okay, so we expect, although we are not 100% sure, that D1 is off. So again, we make an assumption regarding the state of the diode, and we proceed. At the end, we have to come back and see if the numbers that we have found for the voltages and the currents agree with this assumption. All right. So if D1 is off, I can simplify the circuit. So the circuit now reduces to one voltage source, Vx, a diode that is off, so an open circuit, and then everything else is there. So we have R2, R1, and the battery. So we have the battery, R1, R2, node N, and then VB for the battery. That's what we have presently. Okay, so Ix, which is defined as the current drawn by the input of the circuit, is 0. All right, so as long as Vx is negative enough, we don't know how much that is, but as long as Vx is negative enough or not positive enough, Ix is 0 because the diode is off. So that means Ix is 0. Okay, so then I can go ahead and draw the axes like so, Ix, Vx, and I know that for some range of Vx, the diode is off and the current is 0. So for some range, the diode is off and the current is 0. Okay, so far so good. Now let's go ahead and increase Vx towards positive values and ask at what point, for what value of Vx, the diode turns on. Well, this voltage has to go up and up and up until this voltage is more positive than this voltage by 0.7, 0.8 volts by VD on. All right, so we have to raise Vx to a value that is greater than this value by about VD on. Then D1 turns on. Now we know that when D1 is about to turn on, it has a voltage of VD on from here to here, but its current is very small because we are on this little corner here. So because the current through the diode is small, we can assume that still no current is flowing into these branches. So these branches don't feel that the diode has turned on yet, because the diode has turned on, but it doesn't have much current going into these two branches. Okay, so at some Vx, so we'll call it Vx1 again, if Vx equals Vx1, then D1 begins to turn on. But has a small current. Remember, that was the second principle that we talked about before. Okay, very good. Now, given that the current flowing into this branch is still very small, it seems that D1 is not bothering this branch, these two branches. So it seems that I can find the voltage at node N while D1 is not bothering them, meaning that D1 is not injecting any current into this node because the current through D1 is very small. So we know that the value of Vx1 will be equal to Vn, whatever it is, plus Vd on. So we know that Vx1 has to be equal to Vd on plus Vn. This voltage plus this voltage is the voltage that we need to turn on the diode. The only question is, how much is Vn? Okay, well, to find Vn, we will draw this part of the circuit again. Here's R1. Here's the battery, and here's R2. And this is node N. We're trying to find the voltage from here to here. And I have not drawn the rest of the circuit. Why? Because the current coming from the diode is very small. It doesn't bother the circuit. So this circuit is just sitting by itself, deciding on its own voltages and currents. All right, so how much is the voltage from here to here? How much is the voltage from here to here? Well, we have a battery that connects to R1 and then R2. R1 and R2 form a resistive divider. So we can easily write Vn in terms of Vb and R1 and R2. If you don't see it very well, you can redraw the circuit like this. Just put the resistor here, R1, connect it to node N, and then connect it to R2, and then connect it back to the battery. This circuit is the same as this circuit as long as we remember that this is node N. So we see that we have a resistive divider. That means that Vn itself is equal to R2 over R1 plus R2 times Vb. That is the voltage present at this node when we are not disturbing it by anything else. When the current coming from this diode is very, very small, it is as if the diode were an open circuit. It's not quite an open circuit, but the current is just so small that we don't have to worry about it. Okay, so the value of Vx at which the diode begins to turn on, Vx1, is given by Vd on plus R2 over R1 plus R2 times Vb. So that is the value of Vx1 right here somewhere. So the key behind this analysis was to recognize that when the diode is about to turn on, it has to satisfy two conditions. Number one, the voltage from here to here is VD on. That means that the required Vx is equal to VD on plus Vn. And number two, the condition is that if this diode is about to turn on, its current is very small, so it doesn't disturb the remainder of the circuit. The remainder of the circuit can be drawn in isolation, and we can measure this voltage just by looking at this circuit. So that gives us the value for Vx1. What happens as we exceed Vx1? Well, now the diode has turned on, so we replace the diode by its equivalent circuit, one battery, and in series with a short circuit if you want, if we insist. So when D1 turns on, this is the circuit. We have, again, I draw this. You don't have to draw this short circuit. It's sort of silly, but anyway. And then we have a battery representing the diode in the constant voltage model. And then we have R2. Then we have R1. Then we have a battery. And then we have the input, Vx. And the battery is Vb. Okay, we are interested in this current. So what can we write here for this current? Well, this is not that difficult. It's a circuit that goes back to basic circuit theory. It consists of a voltage source here, a voltage source here, a resistor here, a resistor here, and a voltage source here. So you can pick any type of analysis you like. You can write KVLs and KCLs directly. You can write nodal equations if you want. There are various approaches that we can use. What I would do is the following. I will say that if this current is Ix, obviously this current is still Ix, because the current cannot be lost anywhere. It's just flowing through these wires, flowing through the battery, coming out of the battery. So that's still Ix. All right. That's Ix is the unknown. We're trying to find Ix in terms of everything else. Okay, now to find that, what we can say is that this voltage here at node N is the following. So Vn, let's write 1 kVL. This voltage is Vn plus this voltage, Vd on, must be equal to this voltage. So we can say Vn plus Vd on is equal to Vx. All right? Okay. So, now, we also know that the current through R2, the current flowing through R2 from top to bottom, is given by the voltage across R2 divided by R2. The voltage across R2 is Vn. That is the definition of this node voltage, this voltage with respect to this voltage. So Vn divided by R2 is this current. How about this current? Well, this current can be found as this voltage minus this voltage divided by R1. This voltage is Vn. This voltage is Vb. So the voltage across R1 is Vn minus Vb. And divided by R1 is the current through R1. So I wrote the KVL. So that's a KVL. I will also write a KCL. The KCL at this node N is Ix is coming in. So Ix is coming in. It must be equal to the sum of the currents leaving that node, exiting that node. So one current is flowing this way. That current is Vn over R2. So that must be equal to Vn over R2 plus another current that's exiting this node, and that's this current. This current is given by this voltage divided by, this voltage minus this voltage divided by R1. So that current is given by Vn minus Vb divided by R1. All right, so far so good. Okay, so why did I write this KVL? Because I wanted to find Vn in terms of known quantities. Vx is known, that's the input voltage. Vd on is known, so Vx is now known. So I see that Vn is equal to Vx minus Vd on. So that's good to remember. Vn, and that can be substituted in here to find Ix. So we see that Ix is equal to, we have Vn over R2 plus Vn over R1. So we're going to write that as 1 over R2 plus 1 over R1 times Vn. Vn is Vx minus Vd on. Vx minus Vd on. And then we have this term, minus Vb over R1. Minus Vb over R1. And that is the equation for the input current of the circuit. All right, so we just have to see how this current behaves as a function of Vx. Well, we see that the current is linearly proportional to Vx, and the coefficient is just this. Does this look familiar? This is the parallel combination of R1 and R2, but inverted. So this whole coefficient is really equal to 1 over R1 in parallel with R2. So I can say that from here on, we grow linearly, and the slope is 1 over R1 in parallel with R2. That is the slope of the characteristic. And the rest, this multiplied by this and that, these are all just shifts, because this characteristic doesn't go through 0. It is shifted to over here. It has to go through Vx1, and those all account for Vx1. All right, so that is the Ix Vx characteristic of this given circuit. Very well. That was not that difficult, as long as we keep track of when the diode turns on and when the diode turns off. All right, now let me just check everything here. Okay, so I will give you a quiz now. Here's the quiz of the day. Plot Vn versus Vx in that example. So as Vx goes from minus infinity to plus infinity, we would like to plot Vn, this voltage from here to here, this voltage from here to here, as a function of Vx. So I will give you 90 seconds to work on that based on all our findings previously. All right. So what does Vn look like as a function of Vx? Well, we have enough information from the first step of the analysis to plot Vn pretty quickly. So let me change the color of my pen to red. So we have Vx here, and we would like to plot Vn. If Vx is very negative, what happens? Well, the diode is off. If the diode is off, what can we find for Vn? Well, we go back and say, what did the circuit look like when the diode was off? It was right here. This is the circuit. The diode is off. We don't worry about this part of the circuit. It's disconnected. And we just have this part of the circuit. So how much is Vn? Well, we already actually found that. That was the calculation we did before. We saw that we have a resistive divider taking Vb and attenuating it by some factor. So Vn just turned out to be equal to R2 over R1 plus R2 times Vb. So as long as Vx is not positive enough to turn on the diode, Vn is constant, and it is given by R2 over R1 plus R2 times Vb. All right. Now, at some point the diode turns on. We know at what point. So at Vx1, as calculated before, the diode turns on. And Vx1 is this value here. Okay, now what happens to Vn when the diode turns on? Well, we actually have an equation for it from the first step. It is this equation here. It says Vn is simply equal to Vx, but shifted down by some amount, Vd on. That's it. It tracks Vx. It just has a constant difference of Vd on with respect to Vx. So it will look like this, and it has a slope of 1. Now, to visualize what's happening with this minus Vd on, I would like to plot one more quantity here. So let me change the color to maybe black. So let's plot on this plane also another line which is Vx. So V is equal to Vx. So let's plot a line called Vy or Vp is equal to Vx. What does that look like? Well, that would be like this. It starts from here. Of course, it goes through 0. And then it goes like this. And this is Vp equals Vx. And that also has a slope of 1. So what we see is that the difference between Vx and Vx minus Vd on is just a shift, a vertical shift downward. In other words, the difference between these two is Vd on. Otherwise, they don't have any difference. The slopes are the same, it's just shifted down. So we say that the output, that node N, if you want to call it the output, node N tracks the input. As the input goes up, the output Vn also goes up, but it has a shift. Sometimes we call it a level shift. A level shift equal to Vd on. If we did not have the level shift, we just would track it with a slope of 1. But we have a level shift which arises from the diode, which arises from the constant voltage model of the diode. In fact, if we had assumed an ideal diode model where Vd on is 0, then we wouldn't have no level shift between these two. The output would be just this line of Vx. Okay. All right. Does this red characteristic look familiar? Yes, we have seen it a number of times in many different examples. In particular, we saw the same characteristic for the example last time that did not have R2. So how does this simplify when R2 is taken out of the circuit? Well, if we want to take R2 out of the circuit, it means that the value of R2 has to go to infinity. It becomes an open circuit. So if R2 goes to infinity, what happens? This goes to 1, so this constant value is VB. That's what we found in the previous example last time. And then Vx1, as you can see here, becomes equal to VD on plus VB. And that's also what we found out last time. So it's not surprising that this characteristic reduces to the previous example's characteristic if R2 goes to infinity, meaning if R2 goes away. All right, that is a quick example to show you how we handle these nonlinear circuits. Very well, let's move on. If you are interested in additional exercises for yourself, you can, for example, find the current through R2 as a function of Vx, or the current through R1 as a function of Vx, and so forth, or the voltage across D1 as a function of Vx. There are many quantities in this circuit that can be plotted as a function of Vx, and they all have interesting insights behind them. All right, so today we will go on to practical examples of diode circuits, or practical diode circuits. What we have studied so far in the form of examples have been primarily theoretical examples that we concocted so that we could analyze them and understand and improve our analytical techniques. But these circuits do not necessarily have a practical application. These circuits only served to improve our understanding or our analytical techniques. But today we will switch gears to other types of circuits that actually have usage in life. But some of these circuits are more complex, and that's why all of this practice was necessary before we get to these practical diode circuits. As engineers, we would like to understand how these circuits operate and their limitations and their design and analysis. So we're not looking at them as just a bunch of topologies so that we memorize what they do. We want to analyze them. We want to understand how they operate and what limitations they may have. All right, so here are some of the circuits that we will study. We begin with rectifiers. If you remember, we briefly defined rectifiers loosely as circuits that allow, for example, the positive voltages to go through and not negative voltages, or maybe the other way around. Those are generally what we call rectifiers. Why do we study them? Well, because they have many applications, including chargers and adapters, and many other places where we use these for producing, for example, only the positive voltages and blocking the negative voltages. All right. The next type of circuit that we will study are called limiters or limiting circuits. Limiters. So in some fields they call these limiters. In some fields they call them limiting circuits. They are the same thing. And these have various usage. For example, sometimes they're used in FM receivers. One example of an FM receiver is in your radio, your FM radio. They're also used in optical communications. Optical communications. And these are all systems that we will talk about during this course at some point, one at a time, but this is just a list of the applications. Then we will also look at voltage doublers. Voltage doublers take a voltage and double it, as the name implies, approximately, and we can keep doubling, so we can increase the voltage. And one important application of these voltage doublers is in RF receivers, or I should say RF transceivers, doesn't matter, RF receivers, right at the antenna. And then also, for example, circuits such as flash memories, and so forth. Flash memories, the flash drive, the USB flash drive that you use, there's a flash memory inside. Why does that flash memory need a voltage doubler? Well, in order to write information onto the memory, sometimes we need a high voltage in the memory, and that high voltage is not available. For example, if you plug in the flash drive into your laptop or into some other portable device, the voltage that that portable device has may not suffice for the voltage that the flash memory needs in order to write information into its cells. So it generates its own voltage inside, a higher voltage, using circuits such as voltage doublers. Okay, and then another type of circuit that we will study will be level shifts. Which are useful for general circuits, and we'll see what they do and why they are interesting. All right, so each of these will take a while to study. Our objective is to have a rigorous study of what they do and what limitations they pose. So we'll spend quite a bit of time on these things. As we study each of these, not only do we appreciate the application in which they are used, but we also hone our skills in analyzing diode circuits beyond what we have learned so far. So this is a very useful study. And these are just diodes. So you can see that by introducing one component into our library of components, beyond resistors and capacitors and inductors, suddenly we can serve so many applications. We can have so many interesting circuits. These were not possible with the devices that we learned about in basic circuit theory courses. So we see that one device like a diode suddenly helps so much with applications and creating interesting topologies. All right. As you have seen in these analyses, in these examples, I tend to draw the circuit numerous times in the course of the analysis. And you see that I draw it here, then I draw it here, then I draw it here, and so on. This is because if we try to do everything in our head by looking at the original circuit, it is possible that we will make mistakes, especially if we have just entered this field and we are learning how to analyze things. So even though it's a little tedious, it is important to draw every circuit in every state, in every part of the region of operation independently so that we can analyze them carefully. We don't try these to do in our head because we can make lots of mistakes. If you look at the circuit, this diode is abstract. Is it on? Is it off? Is it an open circuit? Is it a voltage source? So all of these have to come out, and that's the best way to do that. All right, so let's go on to rectifiers and analyze and understand what they do. So I will add a page here. And let's see. Okay, add a page here. And then we draw a line in the middle. Okay. All right. Now, in order to analyze rectifiers, we need to have some background knowledge. The background knowledge is a combination of what we learned in basic circuit theory courses and some other concepts. So you have to bear with me for about 5 minutes so that I go over these basic concepts before I go to a rectifier. So here are some basic concepts before we get there. So basic concepts. All right. So remember that we talked before about two types of characteristics for circuits, diode circuits in particular. We said that we can plot the IV characteristic, meaning that we apply voltage, vary the voltage, and measure the current provided by the voltage source to the circuit, Ix as a function of Vx. So we had analyzed circuit to obtain IV characteristics or input-output characteristics. So we have an input, the Vx, we vary Vx, and then there's some voltage or some current somewhere that we will call our output. Why? Well, because it's interesting to look at. So we have also input, output characteristic. All right. But today we will also look at another type of characterizing a circuit. And this is what we call time domain response. So also can analyze by studying the time response. So what does that mean? Well, it means that we have some sort of circuit. You have seen this in basic circuit theory, right? And you apply something at the input, a step, an impulse, a sinusoid, some sort of waveform, and then you see what we get here. So for example, it could be that we apply a sinusoid here as a function of time, and then we would like to see what the output does. So the output, also as a function of time, has something, and that's what we would like to analyze. This is what we call the time response of the circuit. So you can go back to every diode circuit example that I have solved here, and instead of Ix as a function of Vx or V out as a function of Vx, you can assume that Vx is a sinusoid, and then see what we get at the output. That's a very interesting exercise, and I highly recommend that you try that. All right, so remember that in some cases it is beneficial to look at the time response, perhaps in addition to the IV characteristics or input-output characteristics. All right, so that's one important point that I wanted to raise. The other point is the concept of tracking. Well, we have seen this in a few examples, so let me go back to the previous page to show you where we saw it in this example. Well, do you remember that after we solved the circuit when the diode had turned on, we saw that when we look at Vn as a function of Vx, Vn happens to be equal to the input minus Vd on. Right? That's what we found for Vn. Vn was equal to Vx minus Vd on, as we found here. So we say that Vn some voltage in the circuit, tracks Vx. That means whatever Vx does, Vn wants to follow, wants to track it. Of course, there's a level shift. There's a shift between the two, but the shift is constant. So if the input goes up by 2 volts, Vn also wants to go up by 2 volts. But they are different by a certain amount, right? So we say Vn tracks Vx in this situation, in this situation. That's what we call tracking. In another language, we say Vn is pinned to Vx, meaning that wherever Vx goes, Vn is also pinned to it and wants to follow it, again with some constant difference. So that's what we call tracking, and it's good to remember that, because as we will see, this happens a number of times in our analysis of circuits. So tracking means, for example, Vn is equal to Vx minus Vd on. And that means Vn tracks Vx perhaps with a constant difference. So even though the difference is not 0, because it's constant, we still take the liberty of saying that Vn tracks Vx. All right. So that should be relatively easy. The third basic concept that I would like to mention here is quick review of capacitors. Again, this is something that you should have seen in basic circuit theory, but students often have difficulty with capacitors, so I thought I just quickly tell you what we should remember from those courses. All right, so what we do know is the following. If we have a capacitor and we measure the voltage across this capacitor, and then we push a current into the capacitor this way, then this voltage keeps rising because we are putting more positive charge on the top plate of the capacitor. So if you plot V as a function of time, it keeps going up. How it goes up, we don't know. It depends on the behavior of this current. Is it a constant current? Is it a sinusoidal current? Whatever it is. But so long as we push current this way into the capacitor, so long as we push positive charge onto the top plate, the voltage wants to go up. So remember that. Conversely, if we have a capacitor and we take current out of it in this direction, so we keep taking positive charge out of the top plate, then what will happen is that the voltage keeps going down. So V, T, it goes down in some manner. So that's the only qualitative behavior that we need to remember right now. Of course, we know that the current and voltage of a capacitor are related by I is equal to C dV over dt. But for now, all we need to remember is that if we push charge onto the capacitor, positive charge, the voltage wants to go up, and vice versa. All right, so with these principles, we can now go and talk about rectifiers. There are two types of rectifiers, half-wave rectifiers and full-wave rectifiers. So we start with the former. So we're going to talk about half-wave rectifiers. Okay, well, the half-wave rectifier, if I change the color of my pen, is actually something that we have seen in one form or another before, and it's just this. We have a diode, we have a resistor, and R1, D1. maybe we call this from now on V in, and we call this V out. Whenever I write V in here, I mean V in is positive here, negative here, and similarly V out is positive here and negative here. So V in is applied from outside. We have a voltage source that we haven't drawn. We'll connect this point. And V out is what we measure between these 2 points. So sometimes to make sure that we remember this is a voltage source here, we actually draw a voltage source to make sure we don't forget that there is a voltage source applied to this point. It's called V in. But at this point, we are just measuring it. So in our mind, we can put a voltmeter between these 2 points and measure the voltage. Okay. This circuit is called a half-wave rectifier. So we would like to study this circuit from 3 perspectives. IV characteristic, input-output characteristic, meaning V out as a function of V in, and then finally is time response. Time response means this V in has some sort of time waveform, maybe a sinusoid, and the question is, what does V out look like as a function of time? So all of these have to be studied. Now, for the first 2, IV and input-output characteristics, actually we have done it a number of times in different forms, so we can do that pretty quickly, right? Again, we assume a constant voltage model for the diode. All right, so let's start with that. We plot IX. We'll call this IX, or we can call it I in now. It doesn't matter really. I in as a function of V in. All right, so we start with V in at -infinity and come forward. If the voltage is very negative from here to here, this diode is off. So there's no current. There's an open circuit, there's no current. So I in is 0. At what point does the diode turn on? It turns on when this voltage from here to here is equal to VD on. Why? Well, when the diode turns on, when the diode is about to turn on, it needs a voltage of VD on from here to here, but the current through it is small. So if there's any current through the diode, which is very, very small, and it flows through R1, it generates a very small voltage here. So if I write a KVL, I say this voltage is equal to this voltage plus this voltage. So this voltage is VD on. This voltage is very small because the current through the diode is very small. That's our second principle. That means that V in is approximately equal to VD on. So the voltage necessary at the input to turn on the diode is just VD on. So at VD on, the diode turns on. Okay, this pen had a hiccup in it. Let me erase and go back to this color. All right, so VD on, and then that's where the diode turns on. So just to make sure that this point is clear, let me draw the circuit when the diode is about to turn on. So we have VD on here, then we have R1, and if you'd like we can draw that short circuit, and this is V in. So the point is that when the diode is about to turn on, this current is very small. So we say ID is close to 0 because the diode is about to turn on. And because ID multiplied by R1 gives us this voltage is also very small. Therefore, this voltage is equal to this voltage. That is the voltage necessary to turn on the diode. What happens after the diode turns on? Well, we can still use the same model. So the current becomes equal to V in minus VD on divided by R1. So if we call this I in If you want to do it step by step, this is how you would say. I in goes through the battery, goes through R1. So the voltage across R1 from here to here is I in times R1. I in R1 plus VD on is equal to V in. Therefore, I in is equal to V in minus VD on divided by R1. So we'll write I in R1 plus VD on is equal to V in. So I in, which is what we're looking for, is equal to V in minus VD on divided by R1. And that's just a straight line with the slope of 1 over R1 right here. Another way of quickly writing this is to do the following. Remember the concept of tracking? Well, we see that after the diode has turned on, this voltage tracks this voltage, right? It tracks this voltage with a difference of VD on. So as this voltage goes up, this voltage also wants to go up. The difference is only VD on. So what we say is that this voltage is equal to this voltage minus VD on. And now that we have this voltage, we divide by R1, and that gives us the current. So the concept of tracking, the concept that this voltage is pinned to this voltage with a difference of VD on, as shown here, is very useful in analyzing these circuits. Okay, that is the current. The current that we have in the input branch is not particularly exciting, but it's just a quick note here. In the next step, let's go and try to plot V out as a function of V in, the input-output characteristic. All right, well, what does that look like? So input, output characteristic. All right, well, we have V in here, and then we have V out here. What we know is that if V in is negative, the diode is off. If the diode is off, then we don't have any current. We don't have any current. The current through R1 is 0. If the current through R1 is 0, the output voltage is 0. So the output voltage is 0 up to the point where the diode turns on. And that's right here, VD on. Now what happens? When the diode turns on, the output voltage is pinned to the input voltage, or the output voltage tracks the input voltage with a constant difference of VD on. So we say that past this point, what we have is V out is just equal to V in minus VD on. So it's just the slope of 1. So it's pretty simple. The circuit says, if the input voltage is less than VD on, I will block it. I don't let it go to the output. See that the output has nothing, 0. But if the input voltage exceeds VD on, I will let it go to the output in its entirety, meaning that if the input changes by 1 volt, the output also changes by 1 volt. There is a level shift. There's a shift between the two, between the input and the output, right? The input and the output are related by this level shift here. But it's a constant value, and in many cases, it's not a big deal. We just have to remember that. Okay, so we have analyzed the input current as a function of V in and the output voltage as a function of V in. Now we go to the time response of the circuit. And for that, we can apply a sinusoid. Now here things become more interesting, a little more complicated, so we have to be patient about that. All right, so time response. So I will draw a big sinusoid here representing the input voltage as a function of time. So V in. And I will write V in is equal to V0 sine of omega t. Omega is the frequency of the input, 2 pi times the frequency of the input. And V0 is the peak value. So this value here, is V0, the peak amplitude of the input. Now what we would like to find is the output of the circuit as a function of time. Okay, because we have found these characteristics, actually we have a great amount of help with this analysis. So let's change the color of the pen to maybe brown and see what we can do. Okay, well, V in starts at 0 here. You know that when t is 0, sine is 0. So at time 0, we have 0 for the sine. If V in is 0, how much is the output voltage? Well, we can go back to this characteristic and say, if V in is 0, V out is 0. So V out is 0. So far, so good. Now V in starts increasing as a sinusoid. If V in increases, does V out increase? If V in increases, does V out increase? No. V out is still 0. So V out is 0. Up to what point? Well, V out will begin to change only if V in has reached VD on. So at some point where V in has reached VD on, VD on, when V in has reached VD on at some point, it's strong enough, positive enough to turn on the diode, and let the input voltage go to the output. So at this point, the diode turns on. When the diode turns on, so right here, D1 turns on. When the diode turns on, what happens? The circuit reduces to a battery, a resistor, and a resistor, right? So past this point, we have this configuration. In this configuration, the output tracks the input with a difference of VD on. So whatever the input does, the output wants to do the same thing, except that the input and the output are different by an amount equal to VD on. So from here on, this output signal wants to track the input signal, wants to follow the input signal, but there's a vertical difference of VD on. Okay, so what is the input doing? The input is increasing. The output will also increase, except that they differ by an amount equal to VD on. So the output will also increase sinusoidally just to follow the input. And the difference between these two is VD on, just like this difference here. Okay, so this difference is also VD on. All right, so this continues until we start coming back down. Meaning that the input keeps decreasing. So the input went up here, and now it's coming back towards 0. It's coming back towards 0. So at what point does the diode turn off? Well, the diode, the input voltage has to be at least VD on for the diode to be on. So at some point when the input voltage has come back to VD on, right here, VD on, the diode turns off. And when the diode turns off, the output voltage goes back to 0. So the output voltage goes back to 0 here. So we see that this little waveform here is just a little sinusoid, except that it's shifted down. Okay, so what happens past this point? V in comes down towards 0. Well, the diode is off. No current, no voltage at the output. So we see that if the diode is off, there's no current here, the output voltage is 0. And then V in begins to go negative. When the voltage at the input is negative, what happens? Well, if the input voltage is negative, the output is 0. There's no current through the diode. The diode is reverse biased. So the output voltage has to be 0. Now if this sinusoid repeats itself, what does the output do? The output also repeats itself. So we see the same exact waveform in every cycle. So in the next cycle, we'll have a little bit of 0, a little bit of sinusoid, a little 0, and so on. So in response to a sinusoidal input, we have obtained something interesting at the output, which maintains only the positive half cycles. So this is called a half-wave rectifier. It is called a rectifier because it distinguishes between positive and negative inputs, and it's called half-wave because it allows half of the waveform to go to the output and blocks the other half of the waveform. All right, that's called a half-wave rectifier. And it has also some interesting applications, and because our time is up, we'll come back to this in the next lecture. I will see you next time.